Hi, these are notes about chemical equilibrium. There's like an expression that we can write, and then also we can calculate the equilibrium constant KQ and look at what that really means. So, writing a equilibrium expression is pretty easy. What you do is you take the molarity of the product. So the really generic form of this would be that it's going to be your products, and the brackets mean molarity. So they have to be, concentration molarity units over your reactants. But it's not as simple as that. Oops, sorry, my pen's going wild. So if you can have any number of products or reactants. So whatever your products are, the molarity of them, and then also they are raised to the power of the coefficient in front. So if this were a 2, then the concentration of C would be squared. Also realize these are multiplied. So KQ is actually determined experimentally. It does not have a unit, and when you do calculate it eventually, the number value, it's only valid at a specific temperature. So writing the equilibrium expressions, when you do write these, we do not include liquids and solids because they're not, they're uniform, they're pure, they don't really have a molarity or a concentration. So for when I write this expression here, so a KQ expression, remember, is going to be your products over your reactants. If I were to do it, I would have this to the first, and then my reactants, calcium oxide to the first, times the CO2 to the first. But in reality, what happens is this goes to 1, or you could just cancel those from the beginning. So really the KQ expression for this problem is really just 1 over the molarity of the carbon dioxide. So what we're doing is, if you see a solid or a liquid, they don't have a molarity, so we don't include them in the expression. So you wouldn't even need to do this part. Just know that you're not going to include them. And then wherever you had one would become a 1, essentially. So here's another example. So if we write the KQ, just kind of some practice, you could pause the video and try it on your own if you want. So I'm going to do my products, and I'm doing the bracket to show that it's molarity. This one is going to be squared. These are all gases, so they're all going to get included in the expression. And then hydrogen molarity times the fluorine. And you can put these to the first power or not, it doesn't matter. Here's one more example, KQ. So HCN, I'm going to throw this out right away and throw that out right away because they're solids. And then it would be over the HCl molarity. So the meaning of KQ, we're going to calculate it in just a minute. If you think about the expression is products over reactants, so if you get a value greater than 1, that would mean you'd have more of what's in the numerator. So that in that particular reaction, you're going to have more products than reactants. And then also, if it's less than 1, then that would mean you have more reactant than product. And then equal to 1 would mean that you don't really have, we use the word favor. So if we have a KQ of, let's say, 150, we're going to say products are favored. And what that means is we're going to have more product than reactant. So if it's equal to 1, then you're not really going to have one or the other more favored. Okay, so I'm just going to show you an example where we can actually calculate the value of KQ. Just know that whenever you do a problem, you should always include the expression first. And we already did this one in a previous slide, so I'll just do it again quick though. So in this question, they're telling me at equilibrium. So in a lab, it was determined that the concentration of the hydrogen is 0.25 molarity. I'm not even going to include my units because I know that KQ doesn't have a unit, but I'm just subbing in now to this expression. And then the fluorine is 0.25 and the HF is 0.052. So when I calculate this, I get 0.80. So what does that mean? That means this KQ is less than 1. So that means that my reactants are favored. That means I'm going to have more reactant, more of this in the container than this.